Have you ever stopped to wonder where the light actually comes from when you flip a switch in your home? It's something we do every day, almost without thinking, but the process behind it is truly fascinating. It might feel like magic, but it's really the result of electricity traveling through a vast network of wires, stretching from distant power plants all the way to your neighborhood and finally into your home. This power doesn't just appear out of nowhere. It's carefully generated in huge power plants, which are often located miles away from where we live. At the very core of these plants is a remarkable machine called an alternator. It's the unsung hero of our electrical world, quietly working behind the scenes to keep our lights on. Think of the alternator as the beating heart of the power grid, pumping electricity through cables and wires to homes, schools, and businesses everywhere. Nearly all the electricity you use every day, from keeping your food cold in the fridge, to powering your computer, to lighting up your room, comes from these incredible devices. But how does an alternator actually turn motion into electricity? The answer is both simple and ingenious. All you really need are two things: a strong magnet and a coil of wire. These are the basic building blocks of electricity generation. When you move one past the other, you set electrons in motion, creating an electric current that can be harnessed and used. Power plants use all sorts of energy sources: burning coal, rushing water, blowing wind, and even sunlight, to create the motion needed for the alternator to do its job and generate electricity. Whether it's inside a massive power plant, a wind turbine on a hill, or a hydroelectric dam, alternators are spinning right now, working tirelessly to power our world. By understanding how these machines work, you unlock the secret language of energy and gain a new appreciation for the invisible force that powers your life every single day. To understand alternators, we need to talk about electromagnetic induction, a principle discovered by Michael Faraday in the 1830s. Faraday found that moving a magnet near a coil of wire creates an electric current, no contact needed. This invisible force links magnetism and electricity, and it's the foundation of all generators. Imagine pushing a magnet through a copper coil. The movement creates electricity. The key is motion. No movement, no current. Alternators use powerful mechanical energy to create continuous motion, unlike a simple handheld magnet. In a hydroelectric plant, falling water spins a turbine, which turns the alternator. This spinning motion produces a steady flow of electricity, not just a quick pulse. By harnessing this relationship, we convert mechanical energy into electrical energy. The alternator is the perfect machine for this conversion, powering our world with every spin. Now let's look at the alternator itself, a generator that produces alternating current, or AC. AC is what comes out of your wall sockets, and its voltage can be easily changed with a transformer. Power plants generate high-voltage AC for efficient long-distance transmission, then step it down for safe use at home. This ability to change voltage is why AC and alternators became the standard for power grids. Alternators, also called synchronous generators, must spin in perfect sync to keep the grid stable. Whether in a nuclear plant or under your car's hood, the alternator's job is the same: spin and create AC electricity. It's the workhorse behind almost everything we power today. Every alternator, no matter its size or application, is built around two essential components: the rotor and the stator. These two parts work together in harmony to generate electricity efficiently and reliably. The rotor is the moving part, spinning rapidly inside the stationary stator. This spinning motion is crucial, as it creates the dynamic environment needed for electrical generation. The rotor itself acts as a powerful electromagnet. This is achieved by sending a small but steady direct current, or DC, through copper coils that are tightly wound around an iron core at the center of the rotor. This process, known as excitation, transforms the rotor into a strong magnet, with north and south poles, just like a bar magnet. The rotor is mechanically connected to a turbine, often powered by steam, water, or gas, which spins it at incredibly high speeds, sometimes thousands of revolutions per minute. Surrounding the rotor is the stator, which forms the stationary outer shell of the alternator. The stator is packed with multiple coils of copper wire, carefully arranged to maximize efficiency. As the rotor's magnetic field spins past the stator's coils, it constantly sweeps magnetic lines of force across them. This movement induces a voltage in the stator windings, following the principle of electromagnetic induction. The result is a powerful alternating current, or AC, which is the main type of electricity that powers our homes, businesses, and entire cities. The stator's core isn't made from a single block of iron. Instead, it's built from many thin, stacked steel laminations, each carefully insulated from the next. These layers are designed to reduce energy losses caused by eddy currents, which can waste valuable power as heat. By minimizing these losses, the alternator operates much more efficiently. This clever engineering ensures that as much of the generated energy as possible is delivered to the electrical grid, maximizing output and reliability. The seamless teamwork between the spinning rotor and the stationary stator is what enables large-scale power generation, making modern life possible. This simple yet highly effective setup is truly at the heart of every alternator, powering everything from small devices to entire cities. The rotor needs a small DC current to become an electromagnet. But how do you get electricity to a spinning part? Enter slip rings. They transfer power from a stationary source to the rotating rotor without tangling wires. Two metal rings are mounted on the rotor's shaft, each connected to the rotor's field coil. Stationary carbon brushes press against these rings, carrying DC current from the exciter. The current flows through the brushes, into the slip rings, and into the rotor's coils, creating the magnetic field. This setup keeps the rotor energized, no matter how fast it spins. Without slip rings and brushes, the classic alternator design wouldn't work. Some modern alternators use brushless designs, but slip rings remain a simple, reliable solution. They're the vital link that keeps the alternator's heart beating. Let's walk through how an alternator creates electricity. It starts with mechanical energy. A turbine spins, turning the rotor. The exciter sends DC current through slip rings to the rotor, making it a spinning electromagnet. The rotor's magnetic field sweeps through the stator's coils, inducing voltage. As the rotor turns, its north and south poles pass the stator coils, creating alternating voltage. This produces the AC electricity we use. The electricity leaves the alternator through heavy cables, then goes to a transformer to boost its voltage. From there, it travels through transmission lines to cities and homes. This process runs non-stop, powering our lives around the clock. It's a seamless dance of motion and magnetism, delivering energy everywhere. Two key features of alternator output are frequency and voltage. These two parameters are fundamental to the operation of any electrical power system, as they determine the quality and reliability of the electricity supplied to homes, businesses, and industries. Frequency is how many times the current changes direction per second, measured in hertz. In alternating current, or AC, this means the current flows back and forth, switching direction many times each second. In North America, the standard frequency is 60 Hz, while in Europe and many other parts of the world, it's set at 50 Hz. These standards are crucial for ensuring that electrical devices operate correctly and efficiently. Frequency depends on how fast the alternator's rotor spins and how many magnetic poles are built into the machine. The relationship between speed and pole count is carefully engineered to produce the desired frequency. All alternators on the grid must stay perfectly synchronized to keep the frequency stable. If even one generator falls out of sync, it can cause instability or even blackouts across the network. Voltage, on the other hand, is controlled by the strength of the rotor's magnetic field. By increasing or decreasing this field, operators can fine-tune the voltage output to match the needs of the grid. As demand for electricity changes throughout the day, voltage can drop during high usage or rise when demand is low. These fluctuations must be managed to protect sensitive equipment and maintain system stability. The automatic voltage regulator, or AVR, constantly monitors and adjusts the excitation current to keep voltage steady. It acts as a real-time control system, responding instantly to any changes in load or demand. If voltage drops, the AVR boosts the field current to raise it. If voltage rises, the AVR reduces the field to bring it back down. This automatic adjustment happens continuously, second by second. This precise control keeps power reliable and safe for everything from light bulbs in your home to massive machines in factories, and even the city's entire electrical grid at night. The AVR is truly the brain that keeps the alternator's output stable, ensuring that the electricity we depend on is always there, at the right frequency and voltage, whenever we need it. In the early days of electricity, there was a battle between AC, championed by Tesla, and DC, promoted by Edison. AC and the alternator won for large-scale power because its voltage is easy to transform for long-distance transmission. DC voltage is harder and more expensive to change. Alternators are mechanically simpler and more reliable than DC generators, with less wear and tear. They can be built larger and spin faster, producing more power for their size. That's why alternators became the backbone of the global power grid. DC is still vital for batteries and electronics, but AC powers our cities. The choice of AC and the alternator shaped the modern world. The alternator's impact is everywhere. Every time you use electricity, you're relying on one. In power plants, alternators convert energy from coal, nuclear, water, or wind into electricity. Wind turbines and even your car use alternators to generate power. Your car's alternator keeps the battery charged and electronics running. The basic principle, spinning a magnetic field inside stationary coils, hasn't changed in over a century. Materials and controls have improved, but the core idea remains. The alternator is a testament to brilliant engineering, powerful, elegant, and scalable. It converts mechanical motion into AC electricity, ready for transmission. From lighting our homes to charging our cars, the alternator is the quiet hero of modern life. It's the cornerstone of our technological society, spinning behind the scenes to keep our world running.